Okay. Um, we're going to start the wave unit. So let's start with question number one. There are about 100 questions. We'll see how many we get through right now. Which wave diagram has the correct wavelength and amplitude labeled? So that's only a half a wave. That's a half a wave. This looks like one full wavelength, and this looks like one full wavelength. So which has amplitude? That would be C. Remember, amplitude's from mid to top, not from bottom to top. Okay, 2 points. How many wavelengths separate them? Well, one wavelength is that's one wavelength. So that would be a second wavelength. So you're talking 1.5. Answer B. In the diagram below, the distance between A and B is 5 meters. The wavelength is, let's see, that is one wave. That's two waves. So that's 2.5 waves total. 2.5 wavelengths is equal to 5 meters. We solve for lambda. 5 over 2.5. The wavelength is 2 meters. B. Okay. The diagram below shows someone shaking a rope up and down. What kind of wave is traveling in the rope? It's going up and down, and the disturbance is going to the right, so these waves are vibrating perpendicular to the path of the disturbance, so that is going to be a transverse wave. I want to point out that we haven't talked about torsional or elliptical waves, so you're unlikely to see them on this test. Longitudinal wave would be like a sound wave where the vibration goes back and forth like air molecules or a slinky that is compressed. Okay, okay, what's the amplitude? Well, let's see. If from top to bottom is 0.2 meters, the amplitude should be half that, mid to bottom. So the amplitude is going to be 0.1 meters. It's going to be A or B. And let's see, one wavelength, two waves, 2.5 waves. 2.5 waves equals 1.5 meters. So wavelength is equal to 1.5 over 2.5. We can put that into our calculator. 1.5 divided by 2.5. Oh, the decimal place didn't work, but that's okay. Is 0.6. So wavelength is 0.6. So that would be answer B. Okay. A transverse wave passes through a uniform material medium. Material and medium are a little redundant because the material is your medium. From left to right, as shown in the diagram below. I guess it says a material, that means it's not going to be a light in a vacuum. Which direction represents the vibration of the particles? Well, this is a transverse wave, so if you have a particle, it's going to be going up and down because the wave is going to the right, so that would be answer C. Okay. A student strikes the top rope of a volleyball net. Wow, they have a big picture for this question. Sending a disturbance along the length of the net. The disturbance is best described as well, it's obviously some kind of wave, right? You're striking it, and you're striking it only once, so it is not going to be a periodic wave. It's probably going to be a pulse, right? It's one disturbance. A periodic wave would be repeating. Longitudinal would be a compression wave. And I don't get the feeling that this is going to be a compression wave. Although, honestly, the way this is written, you could argue that it's going to have a compression. That's going to be the sound traveling through it. But I think they're actually talking about a physical wave here, like this sort of thing. And it's definitely not an electromagnetic wave. So let's say a pulse, but there will be a longitudinal wave. That would be the sound traveling through it. But not a big vibratory disturbance like that. Okay, as shown in the diagram below, a transverse wave, in what direction will X move as the wave passes through it? Common question that students get wrong, so please, please, please pay attention to this one. It's going to follow the path of the wave as the wave passes through it. So the first thing it's going to do is, as this crest strikes it, it's going to go up. Then when this part reaches the wave, then it will start going down, and it'll go up again at the end. So it's going to go up, and then down, and then up. So let's see which one. Up, then down, then up. D. So it goes up as it goes there, goes down as this part of the wave goes through point X, and then it's going to go up again at the end. A transverse wave moving toward the left. Ooh, a leftward moving wave. For some reason, those are discriminated against a little bit more often. Most waves seem to move right for some reason. Where is the rope moving at point P? So that's point P right there. Well, the thing that is approaching it is a crest. So as the crest gets closer to it, it's going to stay in the crest and it's going to go further and further down. So point P is actually going to be moving downward. This is often not intuitive, just like the last question. So it's going to be moving towards the bottom of the page. Displacement versus time for a particle as a wave passes through a medium. What's the frequency of the wave? The frequency is going to be the number of pulses per second, but you can also look at it in terms of wavelength and frequency. So let's see, velocity is frequency times wavelength. Oh, this is a time thing. Okay. Displacement's not going to matter. All we care about is time. So time for one wave is 0.05 seconds. Now technically, that time is really the period. So period, meaning the time to complete one full cycle of a wave, is 0.05 seconds. While frequency is equal to 1 over the period, which means the period is 1 over the frequency. So if you look on the reference table here, let's find the right page for this. Page 5. Period is 1 over frequency, but that means frequency is 1 over period. They are just inverse of each other. So 1 over 0.05, which I think should equal 20 hertz. 20 hertz. The units would be hertz, which is the same as 1 over a second. So a hertz equals 1 over a second, which is the units here. As a wave travels through a medium, the particles vibrate in the direction of the wave's travel. So in this, the wave is moving to the left, but the particle's going up and down. This one is not doing that. This one is traveling left and right. So if it's vibrating left and right as the wave travels through the material, this is going to tell you that it's a longitudinal wave. Transverse vibrates perpendicular to it. Transverse is what this is, and what this is, where the particle vibrates up and down. Longitudinal would be like a sound wave, or a compression wave, where it vibrates back and forth. What forms of energy can be transmitted through a vacuum? Well, let's think about this. Sound in space, no one can hear you scream, so it's not that. Light clearly can travel through space because it reaches us from the sun, so it's got to be a light. If the frequency of a periodic wave is doubled, the period of the wave will be, well, we should find out that assuming the velocity stays constant, which I think this problem is meant to assume, velocity is equal to frequency over wavelength. So if you're not changing this, but you change the frequency, like you double the frequency, 2f, and v is unchanged, well, wavelength has got to be halved, because then you get the same v. They're inversely related. If you want to write it as f is equal to v over wavelength, you double the frequency, well, you got to halve this in order to get the same value, because they're inversely related. So it's halved. Okay. What is the frequency if its period is, okay, the period is 0.25 seconds, well, frequency is equal to 1 over 0.25, which should be 4 hertz. On to the next page. What is the period of a wave if 20 crests pass an observer in 4 seconds? Well, frequency is crests per second, period is seconds per crest, 4 seconds, 20 crests. Crest doesn't even need a unit, so you can get rid of it. 4 over 20 is going to be 0.2. Period is going to be seconds. There we go. A motor produces 4 waves each second. What's the frequency? So if you're 4 waves per second, it should be the frequency, right? Number of waves per second. 4 waves per 1 second gives you 4 hertz. Okay, a physics student notice that 4 waves arrive every 20 seconds. 4 waves in 20 seconds. Let's try this. 4 divided by 20 is equal to 0.2 hertz. Interestingly enough, 15 and 17 are essentially the same problems. Essentially the same kind of wave. This is saying 20 waves in 4 seconds. This is saying 4 waves in 20 seconds, but this is asking for period, and this is asking for frequency, so they're inverses of each other. Okay. A hertz is defined as the number of cycles per second. Cycles, it's not seconds to complete one cycle, that's the period. Cycles completed in 1 second. You're surfing, or at least your whale is surfing. Surfacing. It has an amplitude of 1.2 meters, and it produces 1 wave every 0.4 seconds. If water travels at 4.5 meters per second, well, let's see. Velocity is frequency times wavelength. That means you want to find the wavelength. Wavelength is velocity over frequency. The velocity over the frequency. So velocity is 4.5 meters per second. The frequency, let's see, it's producing 1 wave every 0.4 seconds, so t is equal to 0.4, so f is equal to 1 over 0.4. This is a little tricky, so that should be 2.5. So 4.5 divided by 2.5 gets you 1.8 meters. There we go. A little extra math on that one, huh? A periodic wave, because it's repeating, has a frequency of 20 hertz. Let's see. Velocity is frequency times wavelength. Well, frequency is 40 hertz. Wavelength is, let's think about this. 2 waves are equal to 3 meters. So wavelength is 3 halves, 1.5 meters. So 40 times 1.5 gets me 60 meters a second. Answer C. What equation correctly relates the speed, wavelength, and period of a wave? Nice little question. Velocity is equal to frequency times wavelength. But they're asking about period. So we have speed here, and we have the wavelength. We don't have the frequency, but we know the frequency is equal to 1 over the period. So velocity should be 1 over t times wavelength. So the question is, which equation gets you some derivation of v equals wavelength over period? Because that is what this equation simplifies to. Velocity is velocity is wavelength over period. Is that in here? Velocity is wavelength over period. Good. It's right there. Answer C. Now, I'm confused as to why it has a capital V there. That is probably a typo, in case you're wondering. A wave completes 1 vibration as it moves a distance of 2 meters and a speed of 20 meters a second. What's the frequency of a wave? Well, let's see. We've got a speed, and we've got a distance. So, and we know that in that it does 1 vibration. There's probably multiple ways to do it. But the frequency is going to be number of waves per second. So we could find the time and say it does 1 vibration in a certain number of seconds. We also know the velocity and the speed. So why don't we instead do it? Let's see. D equals distance is velocity times time. So let's do it this way. So 2 meters equals 20 meters a second times time. So you get time is equal to 0.1 seconds. So that means your time for 1 wave is 0.1 seconds. That would be the period. So frequency is equal to 1 over the period. 1 over 0.1 should be 10 hertz. Answer A. A source of waves and an observer are moving relative to each other. They will detect a steady increase in frequency if. Okay, so interestingly enough, we're getting out of some of the basic wave physical descriptions and calculations, and we're getting onto a phenomenon of some sort that is not in your reference table, so you need to know this stuff. So they're moving relative to each other. You want an increased frequency. This is Doppler effect right here, D-O-P-P-L-E-R. And in order to increase frequency, they need to be moving towards each other in some way. So it says the observer detects an increasing frequency if he moves towards the source at a constant speed. That would give you, oh, this is a little tricky. So that would definitely give you a higher frequency. I'm going to tell you that's not the right answer, and I'm going to come back to it why. If he moves away from him at a constant speed, that's definitely not it. He accelerates towards the source accelerates to him. So again, D moving away is not going to be the same. So interestingly enough, A gives you a higher frequency and C gives you a higher frequency. However, that frequency depends on the relative speeds. So this one is going to be a higher frequency, but it's going to be a constantly higher frequency. And C is going to be an increasingly higher frequency because it's speeding up. And it wants an increasing frequency, so the answer is going to be C. Tricky question there. Okay, a train whistle sounds, train whistle of constant frequency as it leaves the train station. So that means that the train is going at a constant speed. Compared to the sound emitted by the whistle, the sound that the passenger standing on the platform here has a frequency of, well, it is leaving the station, so it's moving away. And if it's moving away and it's going, so it should be a lower pitch. So the frequency should be lower. So it's definitely not C or B. Let's see. The sound is lower because the sound wave fronts reach the platform at a frequency lower than the frequency at which they're produced, or lower because the sound waves travel more slowly in the air above the platform. Well, they don't travel more slowly. They should travel at the same speed. It's because the sound waves reach the platform at a lower frequency. Okay. A radar gun detects the speed of a moving automobile by measuring differences in frequency, blah, blah, blah. This illustrates so again, this is just knowledge. You got to know moving objects, frequency difference is the Doppler effect. A source of sound waves approaches a stationary observer through a uniform medium. Compared to the frequency and wavelength of the emitted sound, the observer detects, let's see. So a source is moving towards the observer. So if they're towards the observer, you should have a higher frequency or a higher pitch. So higher frequency. So C and D are definitely out. Well, if frequency gets higher, wavelength should go in the opposite direction. So it should get lower, or in this case, longer. So a bigger number for frequency means, no wait, sorry. A smaller number for wavelength. So it should be answer A, higher frequency and a shorter wavelength. Bigger, smaller. Okay. 27, an astronomer studies light coming from a star. These are grouped together, so I can almost tell you what this is about before I even read it. The observed light frequencies are lower than the actual emitted frequencies. Sounds like the Doppler effect. So if the observed light frequencies are lower, thus redder, that means that they must be moving away from each other. So the distance between the star and the Earth is increasing because they're moving apart. I'm going to put it opposite directions. Okay. An astronomical body emitting pulses of green light is moving towards the Earth. So if it's moving towards the Earth, you're going to get blue shifting, which is a higher frequency. You got to ask yourself, which of these is a higher frequency? Well, we can go to the reference table for this one just to help us out a little bit. Let's see. We start with green, and we need to go to a higher frequency. Higher is opposite on this. So going from green to a higher frequency means blue or violet. So the answer's got to be B, blue. As a wave travels between 2 points, the wave transfers energy. Energy moves in waves every day. Okay. That's easy. It doesn't transfer mass. Mass move a little bit, but it doesn't actually transfer through the wave. Pulse travels along the rope. The pulse loses energy and its amplitude. Well, for pulses like this, the amplitude is related to the energy. So it loses energy, so its amplitude will decrease. It's not true with every kind of wave. So sound and like a mechanical pulse like this, and these energy is going to depend on amplitude. This is different from light. For light, frequency, a high frequency is going to be more energetic. So there are some differences. Okay, which diagram does not represent a periodic wave? Well, a periodic wave is repeating and constantly repeating at the same pattern. So A's got the same pattern throughout. C has got the same pattern throughout. Might not look like it's a constant, but it is a constant wave. They're just not sinusoidal. B is also constant wave. The one that is different is D. D is not periodic because the waves do not look identical. Which phrase best describes a periodic wave? C, a series of pulses at regular intervals. That's answer C. The spreading of a wave into the region behind an obstruction is called diffraction. Again, a definition you need to know. Anytime you have like an opening or an obstruction, the wave curves, that is diffraction. Okay. Which wave phenomenon makes it possible for a player to hear the sound from a referee's whistle, the open field, even when standing behind the referee? Weird question. I don't like this one very much, honestly. But it is going to be, I mean, it's definitely not the Doppler effect, right? Because that would mean that things were moving. Reflection, no. I mean, you're standing right behind them in an open field, so there's no reflection. It's not going to be any refraction because there's no bending, not different substances. It's actually diffraction. So the idea is that even behind the person's mouth, as they're saying words, right? That's their mouth. Terrible picture, I know. Well, some of that sound waves are going to be diffracted and they're going to bend around, so even behind it you could hear that sound. Diffraction, what wave phenomenon is represented in the diagram? Well, my gosh. Well, it's got to be diffraction. You're going waves in a flat wavefront, hit a barrier with an opening. Notice how the waves change shape, but they continue kind of in the same direction. Diffraction. Okay. Same thing. Oh, wavefronts, they're moving to the right, they go through, they turn circular. Diffraction. But notice how everything sounds the same. Refraction, reflection, polarization. It's easy to not get vocab right. A wave is diffracted as it passes through an opening and a barrier. The amount of diffraction that the wave undergoes depends on both the, well, let's see. It depends on the size of the wave or the wavelength, and it depends on the size of the opening. So for big diffraction, you want a small wavelength or you want a big wavelength or a small opening. So the bigger wavelength is going to have more diffraction, a small opening is going to have more diffraction. So it's going to depend on the wavelength and the size of the opening, not the amplitude, not the speed. Waves pass through an opening in a barrier without being diffracted. This provides evidence that the wavelength is, well, let's use this information. You've got a small amount of diffraction. It says without being diffracted. You probably couldn't have that. You'd have a small amount of diffraction. But a small diffraction means that you're going to have a smaller wavelength or a bigger opening. So big, 10 centimeters is, not a small amount. So that tells you that probably your wavelength is not going to be big. It's going to be quite small. So your wavelength should be much shorter than 10 centimeters. Okay. The diagram below shows waves passing through two openings, A and B. Notice how they both create diffraction, and it's asking for how much longer is the path of AP than the path of BP. It's an interesting way to put it. Note here that there's crests and troughs given. That's important to know, and that this is a crest meets a crest. Crest meets a crest is going to be constructive interference. How much longer is the path of A to P than in B to P? Well, let's start here. One wavelength is there, two wavelengths is there. So we went from the center out to the next crest to the next crest. So that's two wavelengths. How about this one, A to P? One wavelength, two wavelengths, three wavelengths, four wavelengths. How much bigger is 4 wavelengths than 2 wavelengths? Subtract it. 4 minus 2 is 2. Two pulses of equal amplitude approach a point P along a string. When they meet, the vertical displacement will be, let's see, this goes up a value A, this goes down a value A. So you get a positive A and a negative A. You add them together. A minus A is 0. So the answer should be 0. C. Gonna probably stop soon. At least pause. Two pulses traveling towards each other. When the centers of them meet at point X, the amplitude will be, well, let's see, this one goes up +2. This one goes down to -1. So you add those together. This is interference. 2 added to -1 gives you +1. So the answer should be A +1 unit. Okay. The diagram shows two pulses traveling towards each other. This one goes up, this one goes down, so the total amplitude is going to be roughly 0, but notice how the shape is different. So even if the amplitude is about 0, the shape is going to be superimposed on each other. So you're going to have a box going up with a depression in it. So what you're actually going to get is D. Notice how you get the box like that, but it's got a dip in it there, so it looks like the overall up, depression, back down, boom, boom. Which phenomenon occurs at the intersections of circular wavefronts? Oh, I don't even need to read that part. It's got to be interference. Two crests interfering, etc., etc., create bigger waves. The two pulses approaching from opposite directions. Amplitude plus 0.2, amplitude of 0.1. When they've passed, after the pulses have passed through each other, will be the amplitude of each of the pulses. Well, important to know that that is not going to change. B does not affect A does not affect B. When they're passing through each other, the total amplitude will be added together because they're both positive. 0.2 plus 0.1 is 0.3. That's as they're passing. But after they cross over, A is going to go back to 0.2, B is going to go back to 0.1. So the answer should be unchanged, which is answer B. Two waves with the same amplitude and the same frequency pass through a uniform medium. Maximum destructive interference occurs when the phase difference is, well, phase difference is going to be maximum when you have it. 180 would be like a crest to crest. That's not going to work. The maximum would be like a crest to a trough. That's going to be, if the whole thing is 180, that right there, I'm sorry, if the whole thing is 360, that right there is half a wavelength. That's going to be 180, so the answer is going to be C, 180. I think that does it for now. We'll pick up starting from 46 at a different date. Let's keep going with this. We are now on question 46. The diagram shows two sources. We got A and B. They're vibrating in phase on the same medium, so going the same speed with circular wave fronts. So we have wave fronts here. What occurs at point P? Well, let's see. That's a crest. The dark ones are crests. The dots are troughs. You got two crests. So whenever you have two crests, or whenever you have two troughs, either way, so point P or this would both be constructive interference. So that would be constructive interference. Points where you had a crest meet a trough like that, that would be destructive interference. Okay. Diagram, you have two waves of equal amplitude and frequency approaching point P. As they pass through each other, the medium at point P will, let's see, should, if you got transverse waves, probably vibrate up and down. Unless there's something to indicate that it would be a standing wave with a node there, but I don't think that's going to be. Let's think about this. If they are, once they go an extra half wavelength, you get so that you're going to have a crest and a trough passing through at the same time. Then you're going to have a crest and a trough passing through at the same time. So it looks to me like you're going to get a standing wave when they cross, and that standing wave will have destructive interference. This is a tricky question. I don't particularly like this one. So because of that, because whenever you cross 2 points, you're going to always have destructive interference and an equal amount of destructive interference because the amplitudes are the same and the frequencies are the same. P should end up being a node and thus remain stationary. Interesting. Normally I would have guessed it would be A, vibrate up and down, because if you just had one wave, P is going to vibrate up and down. But now we have two waves, and because they are exactly out of phase when they cross each other at point P, it should remain stationary because they're out of phase with the same amplitude and the same frequency. Periodic wave, which points are in phase with each other? In phase is going to be full wavelength apart, so that looks like A and D is one full wavelength. They don't go crest to crest or trough to trough, but they do occur in the same part of the wave, which is on the downslope. A and B. A and C and D are also, if this is 360 degrees, right? A and C are going to be 180, C and D are going to be 180, which would be out of phase. Okay, periodic wave. Which 2 points are in phase? Well, again, in phase is one full wavelength. So A and C are a half wavelength, even though they're at the same height, you want to say. They are only a half wavelength apart, so they would be out of phase. B and E look like they are in phase because they both are one wavelength apart, so the answer is going to be B and E. 2 points on a transverse wave have the same magnitude of displacement from equilibrium, are in phase if the points have, let's see, so 2 points on a transverse wave that have the same magnitude of displacement. So notice how like A and C have the same magnitude of displacement, but they're not necessarily in phase. They are in phase if the points also have the same direction and the same direction of motion, the same direction of displacement and the opposite direction of motion, the opposite direction of displacement and the opposite, in the same direction of motion, the opposite direction of displacement and the opposite direction of motion. This is an annoying question. I don't like this question either, I'm going to be completely honest. But let's just look at this to help us figure this out. So B and E are going in the same direction of motion. If they're one wavelength apart, they have to be moving in the same direction of motion, and they have to have the same displacement. So same direction of motion and the same displacement should work. Same direction of displacement and the opposite direction of motion. So A and C are like the same direction of displacement and the opposite direction of motion. They are not in phase. So it's not B. Same direction of displacement, same direction of motion. That would be A. Okay. Here we got two waves, A and B. The phase difference between A and B is, well, let's see how much different they are. This to this is one full wavelength, right? Now, that means that this is a half wavelength between this and this. That's a half wavelength, so that's a quarter wavelength. So the peaks of wave A and the peak of wave B are a quarter wavelength apart. So wavelength over 4. And if one full wavelength is equal to 360 degrees, so a half wavelength is 180, and a quarter wavelength is 90, so the answer should be C, 90. 52. A tuning fork vibration produces sound waves in air. They are classified as, well, sound waves are probably longitudinal, so it's not going to be transverse, because the air molecules are vibrating, so we need to think about it. For transverse waves, if the wave is going that way, molecules bounce into each other and they vibrate back and forth to the left and right, left and right, left and right, which means they vibrate parallel to the direction of motion. So this says longitudinal because air molecules are vibrating parallel to the direction of motion. It's going to be answer C. This one says perpendicular. That's perpendicular is when they vibrate. If the wave's going to the right, they're going to be vibrating up and down. That's what you're going to get with a transverse wave, kind of like this is a transverse wave. So D is not the right one because longitudinal waves do not vibrate perpendicular. They vibrate parallel. 53. A student plucks a guitar string and the vibrations produce a sound wave with a frequency of 650 hertz. I'm singing this because it's sound, but I don't know the pitch of 650 hertz. A sound wave can be produced as, well, it's going to definitely be longitudinal, not electromagnetic, not transverse. Now, a mechanical wave includes a longitudinal wave like sound, not an electromagnetic wave. So the question is, are they trying to trick us by saying this is a mechanical wave? Because it is a mechanical wave, it just happens to be a longitudinal mechanical wave, because you have physical particles moving. But its frequency is 650 hertz. That tells you it's a constant, it's not changing, so it should be B, longitudinal wave. Just circle that. Okay. As sound passes from water, where the speed is 1.49 times 10 to the third meters per second into air, the wave's speed, well, I'll tell you, we know what the wave's speed is in air approximately. If you look here, we can see, oh, the speed of sound in air is around 3.31 times 10 to the second. That's at STP. It gets a little bit higher at regular temperatures and pressures. So you're talking about 331 to about 343 meters per second, depending on the temperature. This is 149, so the speed clearly increases. So it can't be A. The speed has to increase. Now, so that leaves only answer B. You want to double check this. Does the frequency remain the same? It would be if the pitch remains the same. So, okay, good, that works. Because the pitch is not, the number of vibrations is not going to change. 55. Let me pause for a second. Let's see. An electric bell jar. An electric bell is connected to a battery inside a large jar. What happens as the air is removed from the jar? Well, sound will not travel through a vacuum, so it's going to stop making noise. This says electromagnetic cannot travel through a vacuum. That is false. That's light, electromagnetic radiation. Light can travel through a vacuum. Okay. So as you remove the air, it's going to have less and less molecules to bounce off against. So it's probably not going to get louder. So it's going to have to decrease in loudness. That's amplitude. Is the pitch going to change? Probably not the pitch. It says the frequency of sound waves is lower in a vacuum than in air. That should not be true. The pitch should be the same. The amplitude gets less because sound waves cannot travel through a vacuum. Answer D. A tuning fork oscillates with a frequency of 250 hertz. What describes the sound wave? Okay, so it is going to be not an electromagnetic wave because that's light. It's got to be a mechanical wave. And it requires sound to travel through. It requires air to travel through or some other kind of physical medium too. So it does require a medium. Only electromagnetic radiation can pass through space, so electromagnetic does not need a medium, but sound definitely does. Answer D. An electric guitar is generating sound of constant frequency. It increases in the sound. Okay, increase in which sound wave characteristic would increase in loudness? Well, loudness is related to energy of a sound wave, which is also related to amplitude. So that's going to be amplitude. A standing wave is produced when a guitar string is plucked. What characteristic of the standing wave begins to decrease? Well, the pitch of a guitar string is not going to change after you pluck it. And the speed is not going to change, so it's going to be amplitude. So the pitch isn't going to change, so the frequency is not changing, the speed and the wavelength aren't changing, because those depend on, well, the speed depends on the string itself. So unless you're changing something about the string, like the tension in the string, that's not going to change. And if neither of these change, then the wavelength's not going to change. It's got to be amplitude. It's going to get less and less quiet, less and less loud. It gets quieter as time goes on. Okay, air molecules. What diagram represents the motion of the air molecules? Well, you see the air molecules, you can figure out, oh, that's one wavelength right there. From compression to compression. In between you have the rarefactions. They're going to be bouncing left and right, so the answer is D, as they bounce into each other. A student Number 60. In a band notices that a drum vibrates when another instrument emits the same frequency. This represents, well, no, that's going to be resonance, where waves of one type can cause another object to vibrate. So if you play the right frequency of note, it will cause the drum to vibrate because that's its resonant frequency. 61. Tuning fork causes a second tuning fork to begin to vibrate with the same frequency. Sounds just like the last question. It is not the Doppler effect, which is for moving objects. It is going to be resonance. Now there are nodes related to it, but that's kind of just a tricky question. Because you do have nodes and interference going on to create resonance. I don't like those answers being there, but clearly resonance is the best answer. The superposition of two waves traveling in the same medium produces a standing wave. If the two waves have, so a couple things we need. They need to have the same frequency, and they need to travel in opposite directions. So same frequency in opposite directions. Now you'll notice that D is the same frequency in opposite directions. We really want the same amplitude as well, so that would be B. Okay. Because if they had different amplitudes, you're never going to get a complete node. You're not going to get the null point because they're never going to fully cancel each other out in the same place. Okay. You get something that looks like a bit like a standing wave, I believe, though. Standing waves in water are produced most often by periodic water waves. So often, you need the same frequency in opposite directions, right? So it probably works best when they are reflected from a barrier, meaning they go to one spot, they hit a barrier and go back. So now you have two waves with the same frequency and pretty much are pretty close to the same amplitude, but in opposite directions. So reflection would cause it. Just like when we wiggle a spring and this wave bounces off the end and comes back in the opposite direction, we can create standing waves with the springs. Well, the same thing is true with water waves. Point A is going to be a null point or a node. You notice the standing waves are always drawn like this. The hump things right here from that's one full wavelength, and there are 1, 2, 3, 4 nodes in this particular case, and there's 1, 2, 3 antinodes. 4 nodes, 3 antinodes. The nodes are the null points where you get destructive interference. The antinodes are the big points, the humps and the troughs, the crests and the troughs, where you get constructive interference. And A is going to be one of those nodes that results from destructive interference. Answer B. Okay. A wave is moving to the right side of the page. Which wave could produce a standing wave with the original wave? Well, it's got to have the same amplitude. B and D do not have the same amplitude, and it's going to be in the opposite direction, so it would be C is the correct answer. How many nodes are represented in this wave? Well, let's see. 1, 2, 3, 4. 4 nodes. Answer D. Don't forget to count the points on the end, because those are nodes also. Notice this is 1.5 wavelengths, 1.5 wavelengths that you have here. Same was true for this one, 1.5 wavelengths. Two waves are traveling in the same medium and they interfere to produce a standing wave. What is the phase difference between the two waves at a node? Well, if you have a node, you're going to have destructive interference, which means that they're going to be out of sync by exactly a half wavelength, meaning you should have a crest lining up with a trough. When you get a crest lining up with a trough, you are 180 degrees out of phase. There we go. A ray of monochromatic light is incident on a mirror at an angle of 30 degrees. Notice the normal line is dotted. The mirror is labeled. The angle of reflection is, well, if this comes in and it's 30 degrees compared to the normal, it's going to go out at 30 degrees compared to the normal. So the angle of reflection will be the same, 30 degrees. Always true. 69. A light ray is incident on a mirror. Notice the mirror is labeled. They don't have the normal line here. We could put it. It's actually going along the same direction as A. which represents the reflected ray. You could measure this. Maybe I should get a protractor. But I'm going to guess it's got to be C because those look like the same. B is definitely too small. D is definitely too big. Okay. Here we go. Parallel rays of light incident on an irregular surface. So again, you get stuff coming in, boom, and going out. You'll notice arrows on these. The thing that you do not see is that even though the rays coming in are parallel, like that, that, and that, they're not bouncing off parallel, which means it is not a clean image that you're getting out. A clean image would come from specular reflection, or in this case, regular reflection. This time you're getting diffuse reflection. That could be, for example, light bouncing off a tabletop. You can't really see a clear image in it, but you do see light bouncing off. Diffuse reflection is actually much more common than regular reflection. When a student looks into a plane mirror, she sees a virtual image of herself. When she looks into a paper, no such image forms, right? Light bounces off paper, looks pretty bright white. That's from all reflected light. Which light phenomenon occurs at the surface of the paper? So you got light bouncing off. That's going to be reflection, but it's going to be diffuse because it's not creating an image. 72. A diagram shows air here, a glass window here, light rays coming in parallel. They're going to strike the glass window. When the rays reach the boundary, the light is, let's think about this. You are going to get definitely some reflection because you always get reflection. Reflection is going to come off like this, come off like this, come off like this. So it is definitely going to be reflected. So you can cross out A. But will some of the light rays pass through the glass? Yes, they probably will. That's why you can see through glass. If it was a mirror, it would be different, but light will pass through the glass. Some of it will go like this, like this, like this, and then come back out like that. It will bend toward the normal line because it's slowing down, and so you do get some refraction as well. So partly reflected and partly refracted is what we should get. Reflected, refracted. They threw the word diffracted in to try to fool you. We're not talking about diffraction. Diffraction is when you pass through like an opening or an obstacle that causes the light rays to become kind of circular wave fronts. A light spring is attached to a heavier spring. A pulse traveling along the spring is incident on the boundary. So you got two springs. It's interesting here. Clearly, when one of them hits, some of it is going to go pass through, but some of it probably will be reflected also, because you do have a boundary condition. This is a weird question, but it's going to be just like with light with the springs too, so you're going to get some partially reflected and partially transmitted. If the speed of the wave doubles as it passes from shallow water to deep water, well, let's think about this. V equals wavelength times frequency. Well, the velocity is doubling, right? 2. So if initially that's 1 equals 1 times 1, let's just say, well, you double the velocity, Now, the frequency should stay unchanged. So what happens to the wavelength? The wavelength should double. Because if you double the left, you got to double the right. So velocity doubles and frequency stays the same. The wavelength doubles. A change in the speed of a wave as it enters a new medium can produce a change in, well, example, light passes into glass, it's not going to change color, so its frequency is not going to change. And if the frequency is 1 over the period, or the period is 1 over the frequency, the period is not going to change either. The thing that will change is wavelength, because V equals F times wavelength. So if this changes, but this doesn't, then that means wavelength has to change. What occurs when light passes from water into flint glass? Let's think about this. From water to flint glass. I actually want to look this up on the reference table, prove something. Let's see. Water, 1.33. Flint glass, 1.66. So this has a bigger index of refraction. Bigger N. So if it goes from a smaller to a bigger, it's got to slow down. So its speed has got to decrease. So it can't be C or D. And so we then have to say, well, let's think about this. V equals frequency times wavelength. So if velocity gets smaller, but this doesn't change, boom. So velocity is uh, proportional to wavelength, directly proportional to wavelength. If the left side goes down, the right side is going to go down too. So your wavelength is going to decrease if your velocity decreases. So speed decreases, wavelength becomes shorter, and frequency remains the same, should be the answer. Okay. That's a tricky one. A monochromatic beam of light passes from flint glass into water. Monochromatic meaning one color. That's good because we don't get dispersion. How do the characteristics of the beam of light change? Well, if it's from flint glass into water, which is kind of the inverse one, right? It's going from a big N to a smaller N, so it should speed up, right? Now let's think about this. If it speeds up, V gets bigger. V is proportional to wavelength because frequency does not change. So if this gets bigger, then this gets bigger. So its wavelength should increase. Wavelength increases, good. So it's not A or B. Oh, and it bends towards the normal or away from the normal. So think about this. It's going from a big N to a small N, so it's speeding up. So that means it's going to bend away from the normal. That would be answer D. Think, like, imagine water. Air to water is kind of similar, if that's your normal line, to water to flint glass. Because you're still going from a water to flint glass, you're still going from a small to a big, so it should bend toward the normal. Well, in this case for number 77, you're just reversing that, basically like changing the direction of the arrows here. It's going to bend away from the normal when it gets into a smaller index of refraction. 78. What happens to the frequency and the speed of an electromagnetic wave as it passes from air into glass? Well, it's going from a small index of refraction 1 into a bigger index of refraction, about 1.5. So it's definitely going to slow down. So speed is going to decrease. It can't be A or C. And the frequency should stay the same because the color does not change. So that would be D. 78D. The diagram shows a ray of light passing from air. Notice how it's traveling at exactly that normal line, so your angle of incidence is equal to 0 degrees. When you have 0 degree angle, you're not going to get refraction. It will still slow down, but your direction will not change. So in this case, A, only the speed changes. If that angle was anything else, the speed and the direction would change. Still going to slow down though. Okay, the normal diagram below shows a ray of light passing through two media, medium A, medium B. Okay, so let's think about this. If it bends towards the normal, kind of like with water into glass, let's call this like air into water, for example, bends towards the normal, that means you have a small n to a big N. So that small n to big N means that you're slowing down. So you're going really fast here, and you're going slower. So your speed decreases. How many questions do we have? 116. Gonna have to stop in a minute. Which diagram represents the path of light rays passing through a glass prism? So, ooh, interesting. Okay, this is a tricky one. You're probably not going to see on a test, honestly. Things that you might want to know are that when it comes to refraction, blue bends the most. Refraction. Blue bends the most. So you should get, if white light comes in, blue and purple should bend the most. So in this one, you're not going to get white light out of there. You're going to get White's not gonna go to white and red. White is gonna go to like a rainbow, right? So it's either gonna be, in this case, red bends the most and violet bends the least, or in this one, violet bends the most and red bends the least. Well, we should see that the higher frequencies like violet and blue bend more, so it should be answer A. A certain material, a beam of light has a speed of blah, blah, blah. The material could be blah, blah. Oh my gosh, frequency 5.09 times 10 to the 14th. That's probably a clue that we need to look at this table right here, absolute indices of refraction, because it tells us frequency 5.09 times 10 to the 14th. So speed n equals c over v. So 3 times 10 to the 8th over 2.25 times 10 to the 8th. You end up just getting 3 over 2.25, which gives you n of 1.33. And let's look. What has an n of 1.33? It looks like water does. So this should probably be water. Which quantity is equivalent to the product of the index of refraction of water and the speed of light in water? So a product is multiplying, it's saying n times velocity, and you'll notice the speed of light in water is just going to be v, n times v. Well, if we look at this, c equals n equals c over v, that means c equals n times v, so that's going to equal c, which is the speed of light in a vacuum. D. The speed of light in a material is 2.5 times 10 to the 8th. What's the index of refraction? This does not have this right here, which is okay, because it's not asking us to find the index of refraction and then cross-reference the table. It just wants us to find the index of refraction. So n equals c over v, 3 times 10 to the 8th over 2.5 times 10 to the 8th. The 10 to the 8th will cancel each other out, so you end up getting 3 divided by 2.5, which equals to 1.2. Answer A, 1.2. Notice that there are no units on this. What is the speed of light in a medium having an absolute index of refraction of 2.3? N equals c over v. We need to find the velocity v, so v equals c over n, which is 3 times 10 to the 8th over 2.3. Since 2.3 is smaller, then we can just say 3 divided by 2.3 is equal to 1.3 times 10 to the 8th. I just left the 10 to the 8th out and put it in at the end. So the answer should be B. And it has, this time it does have units, because if speed is in meters per second and n has no units, then velocity will also have meters per second. A ray of monochromatic light is incident at an angle of 30 degrees on a boundary with corn oil. What is the angle of refraction? I'm going to pause the video and come back and do the Snell's law stuff a little bit later, so I have plenty of time to go through this. To be continued. Thank you.